Hello everyone. Let's begin today's class with something you've definitely seen in action: a seesaw in a playground, a pair of scissors in your house, or even a crowbar used by workers. All of these are levers. A lever is simply a rigid bar that can rotate around a fixed point, which we call the fulcrum. It allows us to apply a smaller effort to move a larger load. This is the real beauty of levers. They don't create energy, but they allow us to use energy more effectively. Whether it's cracking a nut with a nutcracker or lifting heavy stones with a crowbar, levers make our life easier by transmitting and multiplying force.
Now, what is the science behind levers? A lever works on the principle of moments. This principle says that when a body is balanced, the total clockwise moment is equal to the total anti-clockwise moment. The mathematical expression is effort multiplied by effort, arm equals load multiplied by load arm. Here, the effort arm means the perpendicular distance between the line of action of effort and the fulcrum. The load arm means the perpendicular distance between the line of action of load and the fulcrum. This is why even a small effort can balance or move a much larger load, as long as the effort arm is long enough compared to the load arm. As you can see in the diagram, the moments balance like a seesaw.
Next, let's talk about mechanical advantage, often written as MA. By definition, mechanical advantage is the ratio of load to effort. So in words, the formula is mechanical advantage equals load divided by effort. From the principle of moments, we can also prove that mechanical advantage equals effort arm divided by load arm. This means that the longer the effort arm compared to the load arm, the greater the mechanical advantage. For example, in a crowbar, the handle is very long, so the effort arm is large. This allows you to move heavy objects with very little effort. Levers come in three different classes based on the relative positions of the fulcrum, load, and effort. Class 1 levers have the fulcrum in between the effort and the load. Examples include scissors, pliers, and a seesaw. Class 2 levers have the load in between the fulcrum and the effort. Examples include wheelbarrows and nutcrackers. Class 3 levers have the effort in between the fulcrum and the load. Examples include tongs and the human forearm when lifting something. Each class of lever is designed for a different advantage. As you can see in the diagrams, the arrangement of effort, load, and fulcrum decides how the lever functions in real life. Now let's explore the velocity ratio, written as VR. By definition, velocity ratio is the ratio of distance moved by effort to distance moved by load. In words, the formula is velocity ratio equals distance moved by effort divided by distance moved by load. For levers, geometry shows that velocity ratio is also equal to effort arm divided by load arm. This is interesting because both mechanical advantage and velocity ratio for levers depend only on the ratio of the arms. But in real machines, friction reduces the mechanical advantage while velocity ratio remains the same. That's why in practice, MA is often slightly less than VR. Let us now solve a numerical example. A crowbar of length 1.5 meters is used to lift a load of 750 newtons. An effort of 150 newtons is applied at one end. The fulcrum is placed 0.3 meters away from the load. Let's calculate mechanical advantage, velocity ratio, and efficiency. Step 1. Effort arm equals total length minus load arm. That is 1.5 meters minus 0.3 meters, which equals 1.2 meters. Load arm equals 0.3 meters. Step 2. Mechanical advantage equals load divided by effort. That is 750 divided by 150, which equals 5. Step 3. Velocity ratio equals effort arm divided by load arm. That is 1.2 divided by 0.3, which equals 4. Step 4. efficiency equals mechanical advantage divided by velocity ratio multiplied by 100%. Substituting the values, we get 5 divided by 4 multiplied by 100%, which equals 125%. But wait! In practice, efficiency can never be more than 100%. This means that in this problem we assumed ideal conditions. In real life, with friction and energy losses, efficiency would always be less than or equal to 100%. Let's wrap up with a quick recap. A lever is a rigid bar that works on the principle of moments. Its performance depends on the relative positions of effort, load, and fulcrum. Mechanical advantage equals load divided by effort, or equivalently, effort arm divided by load arm. Velocity ratio equals effort arm divided by load arm. Levers are of 3 classes, Class 1, Class 2, and Class 3, each with its own unique applications. And finally, efficiency of a lever depends on how closely the mechanical advantage approaches the velocity ratio. From playground seesaws to the tools in your workshop, levers surround us everywhere. They are proof of how simple physics ideas can be applied in daily life to make work easier. I hope you now have a clear understanding of levers and how they function. See you in the next session with another exciting concept in physics.